Mass in special relativity incorporates the general understandings from the concept of mass-energy equivalence. Added to this concept is an additional complication resulting from the fact that mass is defined in two different ways in special relativity. One way defines mass as an invariant quantity which is the same for all observers in all reference frames. In the other definition, the measure of mass is dependent on the velocity of the observer. The term mass in special relativity usually refers to the rest mass of the object, which is the Newtonian mass as measured by an observer moving along with the object. The invariant mass is another name for the rest mass of single particles. The more general invariant mass loosely corresponds to the rest mass of a system. Thus, invariant mass is a natural unit of mass used for systems which are being viewed from their center of momentum frame, as when any closed system is weighed, which requires that the measurement be taken in the center of momentum frame where the system has no net momentum. Under such circumstances, the invariant mass is equal to the relativistic mass, which is the total energy of the system divided by c squared. The concept of invariant mass does not require bound systems of particles, however. As such, it may also be applied to systems of unbound particles in high-speed relative motion. Because of this, it is often employed in particle physics for systems which consist of widely separated high-energy particles. If such systems were derived from a single particle, then the calculation of the invariant mass of such systems, which is an ever-changing quantity, will provide the rest mass of the parent particle. It is often convenient in calculation that the invariant mass of a system is the total energy of the system in the COM frame. However, since the invariant mass of any system is also the same quantity in all inertial frames, it is a quantity often calculated from the total energy in the COM frame, then used to calculate system energies and momenta in other frames where the momenta are not zero, and the system total energy will necessarily be a different quantity than in the COM frame. As with energy and momentum, the invariant mass of a system cannot be destroyed or changed, and it is thus conserved, so long as the system is closed to all influences. The term relativistic mass is also sometimes used. This is the sum total quantity of energy in a body or system, as seen from the center of momentum frame. The relativistic mass is also the invariant mass, as discussed above. Thus, unlike the invariant mass, the relativistic mass depends on the observer's frame of reference. However, for given single frames of reference and for isolated systems, the relativistic mass is also a conserved quantity. Although some authors present relativistic mass as a fundamental concept of the theory, it has been argued that this is wrong as the fundamentals of the theory relate to space-time. There is disagreement over whether the concept is pedagogically useful. The notion of mass as a property of an object from Newtonian mechanics does not bear a precise relationship to the concept in relativity. For a discussion of mass in general relativity, see Mass in general relativity. For a general discussion including mass in Newtonian mechanics, see the article on mass. Terminology. If a stationary box contains many particles, it weighs more in its rest frame, the faster the particles are moving. Any energy in the box adds to the mass, so that the relative motion of the particles contributes to the mass of the box. But if the box itself is moving, there remains the question of whether the kinetic energy of the overall motion should be included in the mass of the system. The invariant mass is calculated excluding the kinetic energy of the system as a whole, while the relativistic mass is calculated including invariant mass plus the kinetic energy of the system, which is calculated from the velocity of the center of mass. Relativistic mass and rest mass are both traditional concepts in physics, but the relativistic mass corresponds to the total energy. The relativistic mass is the mass of the system as it would be measured on a scale, but in some cases this fact remains true only because the system on average must be at rest to be weighed. For example, if an electron in a cyclotron is moving in circles with a relativistic velocity, The weight of the cyclotron plus electron system is increased by the relativistic mass of the electron, not by the electron's rest mass. But the same is also true of any closed system, such as an electron and box. If the electron bounces at high speed inside the box, it is only the lack of total momentum in the system which allows the kinetic energy of the electron to be weighed. If the electron is stopped in, weighed, or the scale were somehow sent after it, it would not be moving with respect to the scale. And again, the relativistic and rest masses would be the same for the single electron. In general, relativistic and rest masses are equal only in systems which have no net momentum and the system center of mass is at rest, otherwise they may be different. The invariant mass is proportional to the value of the total energy in one reference frame, the frame where the object as a whole is at rest. This is why the invariant mass is the same as the rest mass for single particles. However, the invariant mass also represents the measured mass when the center of mass is at rest for systems of many particles. This special frame where this occurs is also called the center of momentum frame, and is defined as the inertial frame in which the center of mass of the object is at rest. For compound objects and sets of unbound objects, only the center of mass of the system is required to be at rest. For the object's relativistic mass to be equal to its rest mass, a so-called massless particle moves at the speed of light in every frame of reference. In this case there is no transformation that will bring the particle to rest. The total energy of such particles becomes smaller and smaller in frames which move faster and faster in the same direction. As such, they have no rest mass, because they can never be measured in a frame where they are at rest. This property of having no rest mass is what causes these particles to be termed massless. However, even massless particles have a relativistic mass, which varies with their observed energy in various frames of reference. Invariant mass. The invariant mass is the ratio of 4 momentum to 4 velocity, and is also the ratio of 4 acceleration to 4 force when the rest mass is constant. The four-dimensional form of Newton's second law is the relativistic energy-momentum equation. The relativistic expressions for E and P obey the relativistic energy-momentum relation, where the m is the rest mass, or the invariant mass for systems, and E is the total energy. The equation is also valid for photons, which have m equals 0, and therefore a photon's momentum is a function of its energy, but it is not proportional to the velocity, which is always c. For an object at rest, the momentum p is 0. Therefore, true only for particles or systems with momentum equals 0. The rest mass is only proportional to the total energy in the rest frame of the object. When the object is moving, the total energy is given by to find the form of the momentum and energy as a function of velocity. It can be noted that the 4 velocity, which is proportional to, is the only 4 vector associated with the particle's motion, so that if there is a conserved 4 momentum, it must be proportional to this vector. This allows expressing the ratio of energy to momentum as, resulting in a relation between E and V. This results in, and these expressions can be written as, and when working in units where C equals 1, known as the natural unit system. All relativistic equations simplify. In particular, all three quantities E, P, M have the same dimension. The equation is often written this way because the difference is the relativistic length of the energy-momentum 4 vector, a length which is associated with rest mass or invariant mass in systems. If m greater than 0, then there is the rest frame, where p equals 0. This equation states that E equals m, revealing once more that invariant mass is the same as the energy in the rest frame. The mass of composite systems. The rest mass of a composite system is not the sum of the rest masses of the parts, unless all the parts are at rest. The total mass of a composite system includes the kinetic energy and field energy in the system. The total energy of a composite system can be determined by adding together the sum of the energies of its components. The total momentum of the system, a vector quantity, can also be computed by adding together the momenta of all its components. Given the total energy E and the length p of the total momentum vector, the invariant mass is given by, in a mathematical system where C equals 1, for systems of particles the total system invariant mass is given equivalently by the following, where, again, the particle momenta are first summed as vectors, and then the square of their resulting total magnitude is used. This results in a scalar number, which is subtracted from the scalar value of the square of the total energy. For such a system, in the special center of momentum frame where momenta sum to zero, again the system mass corresponds to the total system energy, or, in units, where C equals 1, is identical to it. This invariant mass for a system remains the same quantity in any inertial frame, although the system total energy and total momenta are functions of the particular inertial frame which is chosen, and will vary in such a way between inertial frames as to keep the invariant mass the same for all observers. Invariant mass thus functions for systems of particles in the same capacity as rest mass does for single particles. Note that the invariant mass of an isolated system is also independent of observer or inertial frame, and is a constant, conserved quantity for isolated systems and single observers, even during chemical and nuclear reactions. The concept of invariant mass is widely used in particle physics, because the invariant mass of a particle's decay products is equal to its rest mass. This is used to make measurements of the mass of particles like the Z boson or the top quark. Conservation versus invariance of mass in special relativity. Total energy is an additive conserved quantity in systems and in reactions between particles. Finding the sum of individual particle rest masses would require multiple observers, one for each particle rest inertial frame, and these observers ignore individual particle kinetic energy. Conservation laws require a single observer and a single inertial frame. In general, for isolated systems and single observers, relativistic mass is conserved but is not invariant. Invariant mass, however, is both conserved and invariant. The relativistic mass corresponds to the energy. So conservation of energy automatically means that relativistic mass is conserved for any given observer and inertial frame. However, this quantity, like the total energy of a particle, is not invariant. This means that, even though it is conserved for any observer during a reaction, its absolute value will change with the frame of the observer, and for different observers in different frames. By contrast, the rest mass and invariant masses of systems and particles are both conserved and also invariant. For example, this mass is the invariant mass, which is equal to the total relativistic energy of the container only when it is measured in the center of momentum frame. Just as is the case for single particles, the calculated rest mass of such a container of gas does not change when it is in motion, although its relativistic mass does change. The container may even be subjected to a force which gives it an overall velocity, or else it may be viewed from an inertial frame in which it has an overall velocity. In this case, its total relativistic mass and energy increase. However, in such a situation, although the container's total relativistic energy and total momenta increase, these energy and momentum increases subtract out in the invariant mass definition, so that the moving container's invariant mass will be calculated as the same value as if it were measured at rest, on a scale. Closed systems. All conservation laws in special relativity require isolated systems, meaning systems that are totally isolated, with no mass energy allowed in or out, over time. If a system is isolated, then both total energy and total momentum in the system are conserved over time for any observer in any single inertial frame, though their absolute values will vary, according to different observers in different inertial frames. The invariant mass of the system is also conserved but does not change with different observers. This is also the familiar situation with single particles. All observers calculate the same particle rest mass no matter how they move, but different observers see different total energies and momenta for the same particle. Conservation of invariant mass also requires the system to be enclosed so that no heat and radiation can escape. As in the example above, a physically enclosed or bound system does not need to be completely isolated from external forces for its mass to remain constant, because for bound systems these merely act to change the inertial frame of the system or the observer, though such actions may change the total energy or momentum of the bound system. These two changes cancel, so that there is no change in the system's invariant mass. This is just the same result as with single particles. Their calculated rest mass also remains constant no matter how fast they move, or how fast an observer sees them move. On the other hand, for systems which are unbound, the closure of the system may be enforced by an idealized surface, inasmuch as no mass energy can be allowed into or out of the test volume over time, if conservation of system invariant mass is to hold during that time. If a force is allowed to act on only one part of such an unbound system, this is equivalent to allowing energy into or out of the system, and the condition of closure to mass energy is violated. In this case, conservation of invariant mass of the system also will no longer hold. Such a loss of rest mass in systems when energy is removed, according to I equals mc2, where E is the energy removed, and m is the change in rest mass, reflects changes of mass associated with movement of energy, not conversion of mass to energy. The system invariant mass versus the individual rest masses of parts of the system. Again, in special relativity, the rest mass of a system is not required to be equal to the sum of the rest masses of the parts. For example, a massive particle can decay into photons which individually have no mass, but which preserve the invariant mass of the particle which produced them. Also, a box of moving non-interacting particles will have a larger invariant mass than the sum of the rest masses of the particles which compose it. This is because the total energy of all particles and fields in a system must be summed, and this quantity, as seen in the center of momentum frame, and divided by C2, is the system's invariant mass. In special relativity, mass is not converted to energy, for all types of energy still retain their associated mass. Neither energy nor invariant mass can be destroyed in special relativity, and each is separately conserved over time in closed systems. Thus, a system's invariant mass may change only because invariant mass is allowed to escape, perhaps as light or heat. Thus, when reactions release energy in the form of heat and light, if the heat and light is not allowed to escape, the energy will continue to contribute to the system rest mass, and the system mass will not change. Only if the energy is released to the environment will the mass be lost. This is because the associated mass has been allowed out of the system, where it contributes to the mass of the surroundings.